How do you take an infinite-dimensional mathematical object and compress it down to a single number? Collapsing that much complexity risks destroying the underlying linear structure entirely, yet this reduction is the central mechanism of functional analysis. Vector spaces are environments where elements can be scaled and added. Linear operators act as the bridges between them, ensuring that the result of an operation in the first space is preserved once it is mapped to the second. A linear functional is a specific type of operator with a very restricted destination. It takes a vector from space X and maps it to a single point on a one-dimensional line. Its output is always a scalar. While they are often categorized separately, functionals are not a different species of mapping. The algebraic requirements are identical to any other linear operator. The only distinction is that the codomain is limited to the underlying scalar field. This scalar reduction is what allows us to construct dual spaces and define the adjoint operators used to represent observables in quantum mechanics. We can visualize these abstract mappings through geometry. Evaluating a functional is effectively taking a directional measurement of a vector. In a 3D coordinate grid, projecting a variable vector x onto a fixed reference vector A yields a single length on a number line. Slicing space perpendicular to A creates a hyperplane. All vectors ending on this plane project to the exact same scalar value. This leads to Kreyszig's formal definition 2.8-1. A linear functional is a mapping from a vector space into its underlying scalar field, typically the real numbers or the complex plane. Definition 2.8-2 introduces boundedness. For a functional to be bounded, the absolute value of the scalar output must be less than or equal to a constant multiple of the input vector's norm. The output is constrained by the size of the input. By viewing functionals as hyperplanes and projections, we can see them as predictable tools for measuring the orientation and magnitude of vectors. We can test these definitions against 5 common mathematical operations to see which qualify as bounded linear functionals. First, the vector norm. While it produces a scalar, it is not linear. Scaling a vector by a negative number results in a positive length, violating the requirement that f of alpha x must equal alpha times f of x. Second, the dot product. By fixing one factor, the operation becomes linear. The Cauchy-Schwarz inequality proves that the output is bounded by the product of the two vector lengths. Third, the definite integral. Integrating a continuous function over a closed interval maps a function to a single area value. This operation is both linear and bounded by the function's maximum value. Fourth is point evaluation. This extracts the value of a function at one specific coordinate. It is linear, and since the value cannot exceed the function's maximum, it is bounded. Finally, infinite sequences in L squared. If we take the sum of the products of two sequences, linearity is preserved, and boundedness is guaranteed by Cauchy-Schwarz. These examples confirm that functionals are versatile enough to extract coordinates, areas, and angles across varied mathematical spaces. A common point of confusion is whether we must prove continuity and boundedness as separate properties. Kreyszig's theorem 2.83 proves that for linear functionals, these two concepts are mathematically equivalent. If a functional is bounded, its output is physically constrained. This constraint prevents the output from changing infinitely for a finite change in input, which is the definition of continuity. Conversely, because the operator is linear, continuity at a single point, like the origin, implies continuity everywhere. This stability at zero ensures the functional cannot be unbounded. This equivalence allows us to verify the continuity of a functional using simple algebraic inequalities rather than complex topological limits. Theorem 2.8-3 ensures that scalar measurements remain stable. If the input changes slightly, the output cannot jump discontinuously. Because linear functionals can be added and scaled, just like vectors, they form their own vector space. We call this the algebraic dual space, or X star. It contains all linear functionals defined on the original space X. We can extend this logic to the second algebraic dual, consisting of functionals acting on the dual space. This leads to the canonical mapping. We fix a vector in X and treat the functional as the variable input. Observe the transition in the equation, f of x. By rearranging the roles, the vector x now acts as the operator evaluating the functional f. In finite dimensions, this mapping is an isomorphism. Every property of the original space has a direct correspondence in its dual, making vectors and functionals interchangeable. This perspective allows the vector to function as the operator, measuring the properties of the functionals themselves. Linear functionals are mappings that compress abstract vectors into single real or complex scalar values. For these linear mappings, being continuous and being bounded are the same property. These functionals allow us to define the coordinate systems and dual spaces necessary to describe physical states in quantum mechanics. For more rigorous analyses of texts like Kreyszig and Rudin, subscribe to the channel and share this video. Comment below with a specific theorem or chapter you want deconstructed in the next video. Thanks for watching.